Welcome everybody. It's really nice to be here with you guys again this Thursday evening. If you remember, on Tuesday we were speaking about factorizing cubic expressions, and we spoke a little bit about solving, but I just wanted to recap the solving of a cubic equation with you before we jump into the sketching of the cubic function, because we need to be able to solve cubic equations in order to be able to sketch, and I'm going to link the two together now when we are finished. All right, so if we have a look at the equation that is on screen, we've got 2x cubed plus 5x squared equals 3x. What are we going to do with a 3x matrix? What are we going to do with a 3x? If we want to solve
memory, guys.
Can anybody tell me what you think we'd do with a 3x? There we go, into causal. So we're going to take it over to the other side. And
Nice.
now we have the situation. Okay, so of course, we've got to make y equal to 0 if we want to solve for x. Okay, there we go, Lebogang. Perfect. So now every single term in this particular equation, even though it's a cubic, every single term has an x in it. So that means that we can take x out as a highest common factor. So I would be left with 2x squared plus 5x minus 3 equals 0. Right, and now I need to factorize my trinomial. Okay, so I would have 2x in the one bracket, x in the other, and now I've got to think I need my plus 5 in the middle, so I'm going to put 3 over here and put plus 6 minus 1 would give me plus 5, and negative 1 times positive 3 would give me my negative 3 at the end. So there we go. We have got 3 x-intercepts. Either x is 0 or x is equal to 1 over 2, or x is equal to negative 3. Okay, so when you are solving a cubic equation, it can have 3 solutions like this, or it can have 2 solutions, or it can have 1 solution, right? So we're going to speak about the shape of the cubic function tonight, but cubic functions can be shaped like this. So depending where the x-axis is, if your x-axis is here, where the pink line is, can you see then you would have 3 x-intercepts, 3 distinct different x-intercepts. Or you could have your x-axis here, for example. If your x-axis was here, then you would have 2 solutions. All right, and if your x-axis was either way above or way below, so for example, let's say it was down there, then you would only have 1 solution. Okay, so there can be 2 solutions, there can be 3 solutions, or there can be 1 solution to a cubic. Okay, the most likely scenario for you is that you're going to see 2 or 3. Often they have their turning points on the x-axis, but we'll talk later on about what that means and what it looks like for us. Okay, so solving that cubic equation was really straightforward. Let's have a look at something like this, which is going to be a little bit more difficult. Okay, again, what do you think I should do with a negative 16? Yes, Emma Maleng?
Are you not going to transpose?
I am. I'm going to transpose it. So I'm going to take it over to the other side. Thank you very much. Exactly. All right. Now, what's the problem? I say problem in inverted commas. How are we going to factorize this? We can't take out x. So what are we going to do? So in order to be able to factorize, we've got to do, yes, Nolutando?
I'm not sure, but I think we have to open 3 brackets.
Okay, we're going to have to open 3 brackets, but before we can open 3 brackets, we need to go through the process that we were discussing the other night. Okay, so we need to find a linear factor. Okay, so in other words, you want to sub into this equation and you want to find a value that gives you 0 as an answer. Okay, so I'm going to let you guys do that. What gives us 0 as an answer?
Let's try it, guys. Homotso, do you have an answer? You are unmuted.
I've got an answer. Let's see whatever. Okay, Nolutando, you got your hand up again. Do you have an answer?
I think the linear factor is 2.
Absolutely. Okay,
Nice.
so if this equation was f of x equals whatever it is, then what we're discovering is that f of 2 equals 0. What does that mean? It means that x, what 2 is a factor? X plus or minus 2 is a factor. Good, well done. So x minus 2 is a factor. Okay, so now you can see why we needed these skills from the other night. Okay, and now we've got that same situation where we need to work out the values of A, B, and C. Okay, so can anybody tell me how am I going to work out what A is? Can anybody tell me how I'm going to work out A, please? Can you remember, Matrix? How would I work out the value of A? No, Latendo, go for it.
Can I give it a try?
Yeah, of course you can. Go for it.
I think we're going to use ax squared,
And what are you going to multiply it by?
and then it's ax squared. It's equals to 1x cubed.
Okay, so you've got to be careful here, Nolutanda. You've got to multiply x with ax squared to get ax cubed. But you're quite right, it is equal to 1x cubed, so that means that a is equal to?
1.
Lovely. Okay, keep going.
And then we're going to say bx
Okay. Bx squared.
um
Okay, because remember you're
bx squared
multiplying. Good.
bx squared minus
Good.
minus 12x
Minus 2x
minus 12
squared.
minus
Good. And
2x squared
lovely. And what's that going to be equal to?
0.
That's it, 0x squared. Well done. Okay, good job. So what does that mean for after this?
This means
So
we have to find the value of c.
first of all, we have to find the value of b. So you've got bx squared minus 2x squared is 0x squared. So what are you going to do now to work out the value of b?
We're going to equate the equations.
Exactly. So we're going to drop the x squareds and we're going to say b minus 2 is equal to 0.
0,
So that
yes.
means that b is equal to?
2.
Excellent. Good job. Okay, now do the c for me, please.
Okay.
So what are we going to multiply negative 2 with?
I think it's Negative 2c is equals to 16.
That's it. Well done. Negative 2c is equal to 16. Well done. So c would be equal to negative 8. All right. Well done, Nolatundo. That's great. All right. So now we've got x minus 2 times 1x squared plus 2x minus 8. Now we need to factorize our trinomial. This gives us x minus 2. Whoopsie daisy. It's so irritating when it does that. And now we've got to find our factors for x squared plus 2x minus 8. So what numbers are we going to use, Matrix? So two numbers, when we multiply them, it's got to give us 8, but the difference is 2. Well done, Leanne. So 4 will be positive, and 2 will be negative in this case. All right, so how many solutions does this particular equation? Yes, Ayanda, good. How many solutions does this particular equation have? Either x is equal to, no, Nadia, it's only got 2. So either x is equal to 2 or x is going to be equal to negative 4. Okay, because the bracket x minus 2 is repeated. Okay, so even if a bracket is repeated, it's still only one solution because the solution is the same. There we go. Okay. All right, now that means something very specific for us, but I'll get into that a little bit later or maybe in the next lesson with you. Don't know if I'm going to be able to explain that today. All right, but this particular graph only has 2 solutions. So what it means is that this graph is like where I drew the blue line. Okay, one of the turning points is on the x-axis and the other turning point, the turning point lies on the x-axis and there's one other intercept. Okay. All right. So now we've seen where there's only one solution. Where there's 2 solutions. If you had an equation like this, imagine you had x cubed minus 8 equals 0. Then what you could do here is you could take the 8 over to the other side. You could take the cube root on the left and the cube root on the right, and x would only be equal to 2. So there's an example where there is only one solution. Okay, so that cubic only has one solution. This one has 2 solutions. The first one that we looked at had 3 distinct solutions. Okay, so you're expecting a maximum of 3, a minimum of 1, but possibly 2 solutions as well when you are solving a cubic equation. Okay, so let me ask you a question before we jump into the sketching. All right, when you take your equation and you make it equal to 0, y is equal to 0. So when you're solving for x, what information does that give you about the function? When y is 0 and you solve for x, what information does that give you about the function? Can anybody tell me? What do you guys think? Lindelwa, you put your hand up. What does it give us?
Ma'am, I think it gives us like the critical values, the points that we will have on the graph that we're going to sketch.
Absolutely, absolutely. But if y is 0, it specifically gives us the x-intercepts. Okay, but thank you very much for your answer. Let's just have a look what's going on in the chat. Yes, and Tokozo says x-intercepts, and Ntlantla says x-intercepts. Are you not looking for the x-intercept? Yes, you are. Okay, so when you make y equal to 0, you are finding the x-intercepts. Now, we always have to show the intercepts with axes. Okay, so now you know how to do that when you are sketching a function. All right, I'm going to show you how to do the other things just now. Let's just talk about the graph of the cubic function. All right, so every cubic function takes the general form f of x equals ax cubed plus bx squared plus cx plus d. Okay, a cannot be equal to 0, but b can be 0, c can be 0, or d could be 0. All right, the value of d specifically, matrix. Okay, d is the y-intercept. So if you have got a constant, that is the y-intercept of the function. So if we go back up here, the y-intercept of this particular function would be 16. Okay, if we have a look at this equation that we solved, there is no d value. There is no constant term. So that means that the y-intercept is at the origin. Okay, that's the first thing. All right. Now, when we're talking about a parabola, parabolas take the form y equals ax squared plus bx plus c. What happens when a is positive? What shape does your parabola have? What shape is your parabola when a is? Emma Malene?
Can I try it, ma'am?
Yeah, sure. So what shape?
It simply means the graph is increasing.
It doesn't mean the graph is increasing. It's the
It's
shape.
the first shape, ma'am.
So the shape.
When
No.
A is greater than 0.
Okay, but with a parabola. You're right, it's the first cubic function, but with a parabola, it means that the graph is I see a few of you concave up, smiley face. Good. Yes, absolutely. So your graph is that shape. When A is negative, your graph is sad face. Okay, so what that means for us is that we already know from our prior knowledge about functions that A affects the shape of our function. So when we are talking about A, we are talking about the coefficient of the x cubed term. All right. Now, if it is positive, like Emma Maleng was saying, your graph has a very specific shape. First, it is concave down. And then it is concave up. All right. So this bit over here that's like this, that is what we would refer to as concave down. It then becomes concave up after a specific point, and this is what we would refer to as concave up. Okay, so another word for smiley face over here on the right is concave up. Do I have space to fit that in here? Let's try. Okay, so like this, something is concave up. All right, this one over here on this side, sad face, that is concave down. So this idea of concavity is a new one to us because up till this point, we've always been speaking about smiley face or sad face. When A is negative, so in other words, when the value of A, the coefficient of the x cubed term, is negative, the graph changes its shape. It is first concave up, as I'm highlighting on the screen now, and then it becomes concave down. Okay, so very important for the shape of our particular function. So this is first of all concave up, and then it becomes concave down. Come on, silly pen is giving me issues again. All right, so that's the first thing that we need to know. All right, so A affects the shape of our cubic function. If A is positive, the graph is concave down and then concave up. If A is negative, the graph is concave up and then concave down. The value of D is our y-intercept. If there is no D value, if there is no constant, then it means that the graph goes through the origin. Okay. All right. So before we continue, let's just discuss a few features of these particular functions. Okay. So I'm going to first consider a function that's concave down and then concave up. Okay. And I'm going to put in an x-axis over there. It doesn't matter where our y-axis is. Okay. A cubic function is characterized by two turning points. We have a turning point over here in black, and we have another turning point over there in black as well. At the turning points, the graph changes direction. All right, so before this turning point on the left over here, how would I describe the gradient to the left? Let me color in the turning point a different color. Let's make this one pink. So to the left of the pink turning point, how would I describe the graph? Is it increasing or decreasing? Nolatando?
Decreasing.
It's increasing. So as x gets bigger, remember x gets bigger from left to right. So if you were standing over here and you were walking in that direction towards the turning point, are you walking uphill or are you walking downhill?
You're walking uphill.
You're walking uphill, absolutely. Okay, so your function is going to be increasing. So your function is an increasing function. Then we get to the turning point. What's happening to the gradient at the turning point? Exactly, Leanne, it's 0. Okay, because you're not walking up and you're not walking down. So gradient is equal to 0 at your turning point. After you've moved through your turning point and now you're headed towards your other turning point, are you walking uphill or are you walking downhill? Are you increasing or decreasing? There we go, Leanne. You are now decreasing. Well done. And again, when you get to this point over here, this turning point, your gradient is going to be equal to 0. And once you've passed this turning point, as you move to the right-hand side, you are going to be increasing again. So the gradient changes depending where on the function we're at. Okay, so in a cubic function, where in this particular case, A would be positive, the graph is concave down, and then concave up. So we will be increasing to our first turning point, decreasing between our turning points, and increasing after our second turning point. Okay. There is also a point where the graph changes from being concave up to being concave down. Does anybody know what that point is called? Lebogang.
Ma'am, is it the point of inflection?
It is the point of inflection. Okay, so at the point of inflection, that is where your concavity changes. All right, so let's put our point of inflection in blue. Let's pretend that it's over here. There is our point of inflection. And at our point of inflection, concavity is equal to 0. Before your point of inflection, your graph is concave down. After your point of inflection, your graph was concave or is concave up. All right, so all of these points are very important for us in understanding how our cubic function changes, and they're going to be asking us questions about this. Now, those of us that have done calculus at school, they have given us symbols to represent gradient and concavity. What symbol do we use for gradient? What's the symbol for gradient? F prime. Good, Leanne. Okay, so F prime X is the symbol for gradient. Okay, so the symbol for Y is f of x. The symbol for gradient is f prime x. What is the symbol for concavity? Good, Ayanda. What's the symbol for concavity? That's it, William. Lovely. So f prime prime x or f double prime x. Okay, so f prime x represents our gradient and f double prime x represents our concavity. Okay, so another way that I could say that the gradient is 0 at the turning points is how? How can I say the gradient is 0 at the turning points using symbols? That's it, Nhlanhla. Okay, so f prime x equals 0 at our turning points. Okay, so f prime 0 is equal to f prime is equal to 0 at our turning points. How would I indicate concavity at my point of inflection? How would I write that with symbols? Nolitando?
F
That's
prime
it.
C equal to 0.
Okay, so f double prime equals 0, and that's at my point of inflection where my concavity is equal to 0. Okay, good. So I can see you guys have been doing this at school. So that's making sense to us. All right, so we understand all of the symbols and terminology that we use. Okay, so when they write something like this, what does that mean? What does f prime x greater than 0 mean? That's it, Nhlanhla. Well done. Okay, so it means a positive gradient. Good. Well done. Nice. F prime x smaller than 0 means what? Yes, exactly, Nonjabulo. The gradient is the derivative. So f prime x smaller than 0 means that the gradient is negative. Well done. So now, what does f prime prime x smaller than 0 mean? Good. Means concave down. Well done, Matrix. And what does f prime prime x greater than 0 mean? That's it, Lindelware. Okay, it means concave up. Okay, so we need to know this because they're going to use those symbols in the questions that they are asking us. All right, so we need to know what all of that means. Well done, Matrix. Lovely. Okay, so I also just want to mention, I'm going to go and do that on the side over here, that when a function, a cubic function, has its a value smaller than 0, the graph is concave up and then it's concave down. Sorry, I didn't draw that very nicely. Okay, so let's pretend our x-axis is over there. Again, it has two turning points where the gradient would be 0. To the left of the first turning point, it is decreasing. Between the turning points, it is increasing. Over here, it is decreasing. So if I wanted to, maybe what I should rather do here is use symbols. Okay, so I could then say that over here, f prime x is smaller than 0. Here, f prime x is greater than 0. After this turning point, f prime x is smaller than 0. Okay, does that make sense to everybody? Are there any questions? Are we all good so far? Thumbs up, thumbs down, how are we feeling? We all okay? All right, good stuff. Okay. Jane, you want to ask a question?
Yes.
Go for
Yes.
it. Sure.
Like the first part that yeah, the concave down increasing, yeah. I can understand it properly.
What don't you understand?
I'm late in this group, so can you explain it again, because I didn't hear you properly.
Okay, so I'm sorry, I don't understand what it is that you don't understand.
The inflection of the gradient, yeah, that kind of things there.
The inflection of the you mean the point of inflection?
Yeah.
Okay, so what we were just discussing was that at some point on the function, the graph changes from being concave down to being concave up. So here, what I'm highlighting in purple, the graph is concave down.
Okay.
When you get to the point of inflection, the concavity changes. So the graph stops being concave down and starts being concave up.
Up.
That's it. Okay, so that happens at your point of inflection. That's where the graph changes its concavity. The graph changes its direction and stops being increasing and starts decreasing at the turning points.
Oh, okay. Thank you.
Okay, no problem. Okay, all right. So now let's go and have a look at how we would sketch these cubic functions. All right, so take some screenshots here. This is some useful information for you. Okay, so as far as the intercepts with axes are concerned, it's the same old rules that we've always used. For the y-intercept, let x be 0 and solve for y. For the x-intercepts, let y be 0 and solve for x. All right, so this is something that we already know how to do. Okay, what's really new for us, okay, is how we determine the coordinates at the stationary points. At your stationary or turning points is a better word, the gradient is 0. That's why they've said determine f prime x and equate it to 0. Okay, and you are now going to solve for x, and those will be the x coordinates at your turning point. In order to get your corresponding y values, you would substitute those x values into your original equation. Okay, and that'll give you your corresponding y values. Right, so a cubic function can have at most 2 stationary points. It cannot have any more than 2 stationary points. A cubic function can also have only 1 stationary point as well. Okay, so in this particular case, this is also new information for us. if a cubic function only has one stationary point, then this point will also be a point of inflection. Okay, but we'll talk about that later on. Those graphs are a little bit more unusual. All right, if you need to find the coordinates at the point of inflection, what we would do here is we would take the second derivative and we would make that equal to 0. All right, and then solve for x. But I'm going to show you how to do all of that right now. Okay, all right, so let's jump in and go and have a look. Yes, Lebogang?
Ma'am, going back to the note, ma'am, can you please just
Yes,
go back quickly, ma'am?
sure.
Ma'am, I see where it says their maximum or minimum, ma'am. Is that what they refer to, relative max and relative
Yes,
minimum?
absolutely. So a local maximum and a local minimum. Okay, so if we go back up here, all right, this turning point over here that's in pink, that would be your local maximum. And this one over here in black, that would be your local minimum. Okay. Similarly, if you were talking about a graph that was this shape, this point over here would be your local minimum. And this point over here would be your local maximum. Okay. Emma Maleng, if you can't see anything, try logging out and logging back in again. Okay. All right, Lindelwa, you got a hand up? Go for it.
Okay, ma'am. Going back to that graph that you sketched before.
Okay, so the one with this one or the other one next to it? This one.
The other one. Yes,
Okay,
that one.
sure.
So you said that you said that that point there where you wrote local minimum, right after
Yes,
that you said f prime x is greater than 0.
yes.
Isn't that the point of inflection?
No. So when I wrote f prime x is greater than 0, I was referring to the fact that the graph was increasing.
Oh, okay.
Okay, but your point of inflection lies somewhere in between these two. So underneath this, yes, your point of inflection would be somewhere over here. All right. So
Okay.
your point of inflection is always halfway between your turning points.
Okay.
Yeah, 100%. I
Okay.
just didn't put it on there, but that's where it would be located. Quite right.
Thank you, ma'am.
Okay. Yes, 100%. Okay, so for the rest of you as well, your point of inflection is always halfway between your turning points. Okay, so that's why there's two ways to calculate the x coordinate at your point of inflection. Either we can use midpoint formula or we can use the second derivative. So I'll show you that in the example that I'm going to do with you now. Okay, so let's go and have a look at all of these things, how we calculate the intercepts for the axes, the turning points, and our point of inflection. And the graph that we're going to use is this one over here. So x cubed minus 6x squared plus 9x, right? What is the value of the y-intercept? Absolutely. Okay, well done, everybody. Okay, so the value of d is 0, so the y-intercept is 0. So this graph goes through the origin, okay? If we want to calculate the x-intercepts, we know how to do that by letting f of x or y be equal to 0. So 0 would be equal to x cubed minus 6x squared plus 9x, right? This is not really what I want to show you, but let's just go through it and get the x-intercepts. So if d is equal to 0 and we only have terms that have x's in it, we can do what we did in that first example this evening and simply just take x out as a highest common factor. That would leave us with x squared minus 6x plus 9. All right, so this is nice and easy to factorize. So this would be x minus 3 times x minus 3. So there would be how many solutions for x in this case? How many solutions for x do we have? No, not 3. Look carefully. Nolitando, what do you think?
Mom, I have a question.
Okay,
So
go for
can
it.
we also use the first derivative to find the
No, because we're
equation?
finding the x-intercepts. So
Okay.
we don't find the x-intercepts with the first derivative.
Okay.
Okay, so this is what we were doing the other night. Okay, so either x is equal to 0 or x is equal to 3. There are only two solutions. This is the x-intercepts. Okay, so I'm following what we're doing here. We're doing the y-intercept. We've done the x-intercept. Okay, there they are, the x-intercept and the y-intercept. Now we're going to do the turning points. Okay, so at the turning points, remember the gradient is 0. Okay, so for the turning points, we have to use the first derivative. So that means we need to determine f prime x. So this is where our power rule comes in handy. Okay, so we're going to say 3 times 1 is 3, and then we're going to take 1 away from our exponent. And then we're going to say 2 times negative 6 is negative 12, and we're going to take 1 away from our exponent. And then we're going to say 1 times 9 is 9, and we're going to take 1 away from our exponent. So there is your first derivative. Okay, so we have derived the equation that we have been given. We have to indicate that at that point, or at these points, the gradient is 0. So you must let it equal 0. And now we can solve it like we would solve any quadratic equation. Because each of these numbers is a multiple of 3, I can divide through by 3. That would give me x squared minus 4x plus 3. And that should factorize nicely. Okay, so x minus 3 times x minus 1. So either x would be equal to 3 or x is equal to 1. All right, now I see there's some hands up. Nolitando?
Okay, I'm all sorted. Thank you. I'll see it.
You're right. Okay, that's fine. Lebogang?
Oh man, can I just ask from the x-intercepts?
Mm,
Why is it
yes.
2 solutions not 1? Doesn't it mean
Because you've
that-
got either x is 0 or you've got 2 brackets where you've got x minus 3. So if you've got 2 brackets that are the same, then that's only one solution because the solutions are not different.
Oh, thank you. I'm sorry. I thought
Oh,
like it
okay.
was
No,
so-
that's okay. That's why you're here. You must ask questions. It's not a problem. Okay, not a problem at all. All right, so matrix, very important here. Okay, I'm just going to say this again. You must show that your first derivative is equal to 0. You're going to get a mark for that. Okay, so very important that you show that the first derivative is 0. So you're going to take the first derivative, you're going to make it equal to 0, you're going to factorize, don't leave off the equal 0, and there you go. There are the x coordinates at the turning points. In order to find the corresponding y's, we sub back into the original equation. So our original equation is y equals x cubed minus 6x squared plus 9x. Okay, so to find the y coordinates at the turning points, so for the y coordinates at your TPs, you must sub back into original. Okay, because these points lie on your original cubic function. Okay, so what we would do here is we would actually set it out like this. We would sub in f of 3. Okay, now we already know what f of 3 gives us because x minus 3 was one of the solutions for our x-intercepts. So we know that when we sub in 3, we're going to get 0 as an answer for y. Okay, so 3 cubed minus 6 times 3 squared plus 9 times 3, that gives us 0. What we don't have is this one over here. So we need to work out what f of 1 is. Okay, so that would be 1 minus 6, which would be negative 2. Sorry, I'm talking nonsense. Negative 5, and negative 5 plus 9 would give us 4. So therefore, the coordinates at the turning points, guys, when x is 3, y is 0. And when x is 1, y is 4. Khomotso? Khomotso, what's your question? Okay, Khomotso, I can't hear you. If you've got a question and you do want to speak, you're welcome. Emma Maleng?
Khomotso, you can also put it on the chat. then we can see it.
Absolutely. All right, so what I'd like to do is just sketch this very quickly because I don't want us to run out of time, okay? And then I will take some questions. Okay, so now we have to consider, all right, the shape of our function. In front of our x cubed, it was positive 1. So that means that a is greater than 0. So our graph is concave down, and then it is concave up. It's going to take that shape. Okay. Over here, that is where our 1 and our 4 would be. And over here, that is where our 3 and our 0 is going to be. But we can see that our turning point is 3 and 0. And one of our x-intercepts is also 3 and 0. So what happens here is that the graph has its turning point on the x-axis. So in other words, it's going to look something like that. The x-axis is going to be over there. All right, so this point over here is the point 3 and 0. This point over here is the point 1 and 4. Now we have to consider what our y-intercept was. Oh yes, remember it was 0. So that means that this graph goes through the origin as well. Okay, now I see that there are a number of hands up. What's wrong, guys? Okay, Khomotso's hand is still up. Jane, your hand is up. Okay, because our other x-intercept was 0. Okay, so we had 0 or 3. It also went through the origin. So that is what our graph is going to look like. Okay. All right, so let's try and take some of these questions. Okay. Jane, go for it.
Like, ma'am, the screen was black. I couldn't see anything, so I had to leave the group. Can you please start over where the turning point, and the turning point using the derivative?
Okay, so do you mean up here?
Yeah.
Oh, okay. All right, that's fine. I'll explain that again. Let's just see. Lebogang, what was your question?
Ma'am, do we always have to work out the point of inflection, or is it sometimes?
No, so you only work out the point of inflection. It's not a point that you have to show when you sketch the graph. Okay, so but you have to show the coordinates at the turning points and the intercepts with axes. The coordinates at the point of inflection, the y coordinate is unimportant. The x coordinate is important because that's where your concavity changes. But you would normally do that in a question that you've been asked. It's not something that you would generally show on your sketch. Okay. All right, let's just see what the other questions are quickly. Nolatando?
So, ma'am, the reason why okay, I see the y-axis is not exactly on the graph.
What do you mean?
So, like the one is like the line, the black line of the y-axis is not
Yes.
exactly on the graph. It cuts on the zero, on
It
the
cuts
zero
at
x
0
intercept.
and 0, and then it's got its turning point at 3 and 0.
So is it because that our turning points are all positive?
What do you mean our turning points are positive? So do you,
What I'm asking,
yeah, so yeah.
what I'm asking is that because the line of the y-axis only cuts on the x-intercept of 0,
Yes.
and the other points are not on the side of the y-axis.
Yes. So in other words,
So
your turning points are in the first quadrant.
okay.
Okay. All right. Let's just see who was next. Lindelwa?
Ma'am, I would like to ask, the turning point where it says 1 and 4, and
Yes.
down there where it says 3 and 0,
Yes.
can it be vice versa, or that's the way it should be?
Well, it can't be vice versa for this particular function.
Okay.
Okay, so this particular function only has 2 turning points. The one is at 1 and 4, and the other one is 3 and 0. It can't be anything else. And you can't swap them around with one another because then it wouldn't make any sense.
Okay.
Okay.
Thank you, ma'am.
All right, no problem. Okay, so in the chat, there was also, Khomotso, you asking, how do we get the turning point? So that was what this was all about, Khomotso. Over here, where I was talking about the turning points. You have to use the first derivative. So all of this over here was me explaining how you get the coordinates at the turning points. Then over here, this was me explaining how you get the y coordinate at the turning point. Okay, Leanne, you're asking about 1 and 0. What is 1 and 0? 1 and 0 is not a point on our graph. So what do you mean by 1? What do you mean by this? Leanne? The x-intercept. Okay, we didn't find an x-intercept that was 1. Our x-intercepts were 0 or 3. So if our x-intercept is 0, then the coordinates at that x-intercept would be 0 and 0, which would be the origin, or it would be 3 and 0. Okay, which is here. There's 0 and 0, and there's 3 and 0. Yes, Ntokozo.
Ma'am.
Yes. Who's talking? Can someone?
Ma'am.
Yes, Emma Maleng?
Imameleng, ma'am.
Sure. Emma Maleng, what's your question?
Ma'am, could you please go? Ma'am, could you please go back a little bit? Because I'm confused whereby you have said the y-intercept. I don't know if you can hear me or is it my network?
I can. No, I can hear you.
Yeah. Okay, at the y coordinates at turning point must sub back into the origin. Can you see that example?
Yes.
So my question is, are we gonna substitute the coordinates of the y? Or what are we substituting there? What are we actually looking for?
Okay, so are you talking about the coordinates at the turning point? So you've got to be clear about what it is
Yes,
that you.
ma'am. Because
Okay,
I
so you're
saw
talking about
that
the coordinates at the
you have
turning point. Okay,
written y coordinates.
all right. So after you take your first derivative and you make
Yes,
it
ma'am.
equal to 0, you solve for x. That's what I'm doing over here where the purple arrow is. Here's the first derivative.
Okay.
You make it equal to 0 because at the turning points the gradient is 0, and you solve for x. Those are the x coordinates at the turning points. Then in order to get the y coordinates at the turning points, you have to sub the x's into the original equation. So that's why I've subbed in the 3 and I've got 0. And that's why the one turning point is 3 and 0. And then I've subbed in the 1. Subbed in the 1 over here, and I've got 4, and that's why the other turning point is 1 and 4.